Right now, as you're watching this, a star that has guided sailors, inspired poets, and defined the night sky for thousands of years might already be gone. And you wouldn't know it. Nobody would. I'm Fact Spark. If that kind of thing messes with your head, subscribe, because we do this every week. Here's something nobody tells you. The sky you look up at every night is a lie. Not a metaphor, not philosophy, a literal, physical lie. The light reaching your eyes left its source hundreds, sometimes thousands of years ago. You are not seeing the universe as it is. You are seeing its ghost. And here's where it gets uncomfortable. Some of those stars you can name, the ones drawn on maps, printed in textbooks, tattooed on people's arms, they may not exist anymore. The universe just hasn't bothered to send us the memo yet. We've spent millennia treating the night sky like a ceiling. Fixed, permanent, a cosmic wallpaper that would outlast everything. Our civilizations, our species, our sun. We name constellations, we build myths around them, we use them to navigate oceans. But what if the ceiling has an expiration date? Let's start with the star that almost broke the internet. Betelgeuse, the bright orange shoulder of Orion, probably the most recognized constellation in human history. In recent years, something strange happened. It dimmed, dramatically. Scientists scrambled, forums exploded. People genuinely started asking, is this it? Is Betelgeuse about to go supernova? The answer is maybe. And that maybe contains a terrifying detail. Betelgeuse sits roughly 700 light years away from Earth. That means the light we see today left that star 700 years ago. If Betelgeuse exploded last Tuesday, we won't know for 7 centuries.
The star could be dead right now, and tonight you'd still see it shining in the sky like nothing happened. And here's what that explosion would actually look like, if it happened. Or when it happens, because it will. For several months, the night sky would host a new source of light, brighter than the full moon, visible in daylight, a blue-white torch burning in the constellation of Orion. Magnificent, unprecedented in modern human history. And then it would fade, slowly. The debris would scatter and dim, and where there was once a bright orange star, nothing. Darkness. Orion would be missing a shoulder. Every star map ever printed, every mythology ever written, every tattoo of that constellation, instantly outdated. Permanently wrong. Here's the question I want you to answer in the comments before this video ends, and it's something I genuinely think about. If Betelgeuse exploded yesterday, and we won't find out for 700 years, does that change how you feel about the night sky tonight? Does knowing you might be looking at a corpse change anything for you? This wouldn't even be the first time humanity watched a star die in real time. In the year 1054, astronomers across China, Japan, and the Arab world independently recorded a new star appearing suddenly in the sky, bright enough to see during the day. It lasted for weeks. They didn't know what it was. No one did. Some thought it was a divine sign. Others just wrote it down with careful precision and moved on. What they had witnessed was a supernova, a massive stellar explosion. And where that new star appeared, today we see the Crab Nebula, a cloud of expanding gas and dust that didn't exist before that year, the remnant of a death.
A permanent scar in the sky that humans unknowingly witnessed being born. The universe writes its history in light, and we only get to read it centuries late. But you don't need stars to explode to see the sky changing. Some of it is happening right now, so slowly that we forget to look. Barnard's star. Probably not a name you've heard at parties, but it holds a record. It's the fastest moving star visible from Earth. It moves through our sky at 146 kilometers per second relative to the sun. That sounds enormous, and it is. But because of the distances involved, from our perspective, it shifts by the width of a full moon every 174 years. Not impressive over a weekend. But think about a human life. If you're young right now and you locate Barnard's star tonight and you find it again when you're old and close to the end, you will be able to see with your own eyes that it has moved. The sky will be measurably different from the one you were born into. Now scale that up. Give it 100,000 years. Every single constellation you've ever learned, gone. Rearranged beyond recognition. Ursa Major, Orion, Cassiopeia, unrecognizable. The star maps of the far future will look like a completely different universe. The sky is not a ceiling, it's a river. It just moves so slowly we mistake it for stone. And speaking of things we mistake for permanent, let's talk about mountains. Mountains feel eternal. You're born, they're there. You die, they're there. They were there for your grandparents, and they'll be there for your grandchildren. We build entire spiritual traditions around their permanence. Except they're not permanent. They're just slow.
You've probably heard that New York and London move apart by about 2.5 centimeters every year. That's the North American and Eurasian tectonic plates separating, with new ocean floor constantly being created at the mid-Atlantic ridge. It's happening right now, under thousands of meters of water, silently and continuously. But here's the part that changes how you understand earthquakes, and this is worth paying attention to. If the ocean floor is constantly being created and Earth isn't getting bigger, then something has to give. In some places, plates collide and one dives beneath the other, subduction zones. In others, the plates crumple against each other. The accumulated pressure of decades, sometimes centuries, of slow movement suddenly releases all at once. That release, that sudden jump, is an earthquake. And in that moment, the ground can rise by meters. Literally. You can watch mountains being built in real time. The geological process that we assumed required millions of years of invisible creep actually happens in violent, visible bursts. A single earthquake can raise the landscape by 2 or 3 meters in under a minute. If you live in a seismically active region and you're paying attention, you can compare photos from your childhood to photos from today and see a landscape that has measurably changed within a single human lifetime. There's another way land rises that's even stranger, and it connects back to something that happened 12,000 years ago. During the last ice age, enormous ice sheets, in some places several kilometers thick, pressed down on continental landmasses in the northern hemisphere. Ice is heavy.
We don't usually think of it as a rock, but weight is weight, and those ice sheets literally pushed continents downward into the mantle beneath them. Then the ice melted, and the land, relieved of its burden, began to float back up, like a compressed sponge slowly expanding, like a buoy released from the bottom of a pool. This is still happening, right now. In Scandinavia, Canada, parts of northern Russia, the land is rising. In the most extreme zones, it's lifting by nearly 2 centimeters per year. In a single human lifetime, a coastline can rise by more than a meter. There are beaches in northern Canada where old shorelines are clearly visible as raised terraces on hillsides. The ocean's former edge, now high and dry, a record of geological time written in rock and sand. The ground you stand on is not fixed. It never was. We just live too briefly to notice. And sometimes, geography changes not over millennia or centuries, but overnight. In January of 2020, a powerful storm system moved through the Mediterranean coast of Spain. The storm, known as Gloria, battered the Ebro Delta, a landmass that had been building slowly over centuries, shaped by sediment carried down from inland Spain and deposited at the river's mouth. Maps of that delta had been essentially stable for roughly 500 years. In a matter of hours, Gloria severed a long sandbar from the main body of the delta. A peninsula became an island. 5 centuries of cartographic history became obsolete before the storm had even passed. And if watching land disappear is strange, watching it appear from nothing is stranger still.
In November of 1963, fishermen off the coast of Iceland reported something alarming. The sea itself seemed to be on fire.
Smoke and steam rising from the ocean's surface. Then something darker. Then something solid. A volcano on the ocean floor had breached the surface. Over the following days and weeks, an island rose from the Atlantic. Surtsey, named after a Norse fire giant, grew from nothing to a substantial landmass in a matter of days, the lava cooling almost instantly upon contact with the freezing North Atlantic water, building a foundation fast enough to outpace erosion. And what happened next turned that island into possibly the most scientifically valuable piece of real estate on Earth. Scientists established a near-total quarantine. Access is restricted to a tiny number of researchers who arrive in sterile conditions with protocols comparable to those used for planetary protection to prevent contamination of other worlds. The reason? Surtsey is a blank canvas. Life had to colonize it from absolute zero. No soil, no seeds, no insects, no birds. And then, gradually, all of those things, arriving in sequence, building an ecosystem from scratch in front of human eyes for the first time in recorded history. By 2004, the first earthworms had arrived. Plants followed. Then birds began nesting. A fully functioning ecosystem is assembling itself on an island that didn't exist 60 years ago. We are watching evolution run its opening chapters in real time. Which brings us to evolution itself, the process we intellectually accept but rarely actually see. We tend to imagine evolution as something that happens in the deep past, over timescales so vast they're meaningless to a human brain. The fish that grew legs, the dinosaur that became a bird, ancient, invisible, slow beyond comprehension. But it's not slow.
It just usually works below the threshold of a single human lifetime. Consider what happened in a small Italian village called Limone sul Garda on the shore of Lake Garda in northern Italy, right in the region of Lombardy, famous later for very different reasons. About 400 years ago, a genetic mutation appeared in one couple living there, a mutation in a protein called ApoA1 Milano. That protein, in its mutated form, does something remarkable. It eliminates the harmful effects of bad cholesterol. Carriers can eat poorly, live without particular discipline, and their cardiovascular system remains essentially protected. The mutation spread through the village's small, relatively isolated population. Today, dozens of Limone's roughly 1,000 residents carry it. The pharmaceutical industry has spent enormous resources studying and trying to replicate what this mutation does naturally. A random copying error in one person's DNA 400 years ago is now at the center of cardiovascular medicine research worldwide. That is evolution. Not in the fossil record, not in ancient history. 400 years ago. 13 generations. The blink of an eye on any biological timescale. And yet here it is, reshaping medicine in the present. And if a beneficial mutation can spread through a population in that time, the same process runs constantly in pathogens. A virus mutates. Most mutations are failures, dead ends, versions of the virus that can't replicate efficiently. But occasionally, by pure probability, a mutation lands in exactly the right configuration to allow the virus to do something it couldn't do before. Jump to a new host species, replicate faster, evade an immune response. Every time a virus replicates, it's running an evolutionary lottery. Most tickets lose, but there are billions of tickets, and the lottery never stops. Even language evolves in front of us, and this is the one we participate in without realizing it. Think about your closest friendships, or a long-term relationship. Over time, almost certainly, you've developed words, inside references, modified versions of real words that only make sense in that specific context. Sounds or phrases that carry enormous meaning to the people in the group and are completely opaque to everyone outside it. That is not just a cute quirk. That is the first stage of language formation. Take a group, isolate it sufficiently, And given enough time, those private words multiply. Grammar subtly shifts, pronunciation drifts, and eventually you have a dialect. Then a language. Then, given centuries more, a language family. Today, full isolation is nearly impossible. The internet connected everyone, and that connection killed most of the conditions that allow new languages to emerge. A dialect that might once have developed into something entirely distinct now gets flattened by constant contact with the wider linguistic world. But the internet didn't stop language from evolving, it just changed the scale. Instead of isolated villages developing private languages, billions of people are now collectively shaping a global one, in real time. Written internet language has its own grammar, its own syntax, its own vocabulary that didn't exist 30 years ago. Entire modes of expression, the architecture of how people write to each other, have been invented and standardized within a single generation. You are participating in the largest linguistic event in human history every time you type a message.
And even time itself, the way we measure it, isn't immune to impermanence. Atomic clocks are the most precise instruments humans have ever built. They measure time by counting the vibrations of atoms, cesium typically, oscillating at over 9 billion cycles per second. They are so accurate that they wouldn't gain or lose a second in 300 million years. And yet, even radioactive atoms decay. Uranium, for instance, takes roughly 4.5 billion years to lose half of its mass to radioactive decay. That's approximately the age of Earth itself. The uranium atoms that exist today were forged in stellar explosions before our solar system existed, and they are slowly, continuously, inevitably breaking down. You can detect it. Hold a Geiger counter near uranium ore and you hear it. That ticking isn't just a sound, it's time itself dissolving at the atomic level. Everything we call eternal is, at the most fundamental level, made of processes with an end date. The stars, the mountains, the continents, the atoms. Even the most permanent things are just collections of very slow moments. So what does that mean for us? We are the brief ones. 70, 80, 90 years if we're fortunate. A rounding error in geological time. A single frame in the film of stellar evolution. Your life, from the inside, is not brief. It is complete. It is everything you will ever feel, everyone you will ever love, every moment of joy or loss or wonder you will ever experience. From your perspective, it is total. It is your entire universe. Call it an eternal instant if you want. It sounds poetic, but it's also just accurate. The question isn't whether your life is long relative to a star. Of course it isn't.
The question is what you do with a finite piece of time in a universe that is, despite everything, mostly just waiting. Which brings me back to where we started. Betelgeuse might already be gone. The constellation you grew up with might already be different from the one your descendants will see. The mountains outside your window are at this exact moment either rising or eroding. Languages are shifting. Ecosystems are assembling on islands that didn't exist within living memory. Evolution is running its lottery in the cells of every living thing on the planet. All of it is moving. All of it is changing. All of it has an end. And somehow, in the middle of all that relentless impermanence, you get to be here, aware of it, watching it, asking questions about it. That's not nothing. That's actually, when you think about it, a remarkable place to be standing.